One of the smartest humans who ever lived figured out why things fall, and his answer had nothing to do with a force pulling them down. Richard Feynman was not your typical scientist. He cracked safes for fun. He played bongo drums. He helped build the atomic bomb when he was barely 24 years old. He won the Nobel Prize in physics. And when he explained things, he did it in a way that made you feel like you had been lied to your entire life. Most people think gravity is simple. Heavy things pull on lighter things. The earth pulls on you. The sun pulls on the earth. Done. That is what school taught you. That is what Newton told us over 300 years ago. But Feynman understood something deeper, something Einstein had discovered but never explained in a way normal people could feel in their gut. Feynman looked at gravity and said the real reason objects fall has almost nothing to do with space bending or forces pulling. It has to do with time. Time itself flows slower near heavy objects. And that tiny difference in the speed of time is the actual reason you are stuck to the ground right now. That probably sounds impossible, but by the end of this video, you will see exactly what Feynman meant. And once you do, you will never look at a falling object the same way again. Let me explain. The equation that found a planet. For over 300 years, one man's idea about gravity ran the entire world. His name was Isaac Newton, and his equation was so good that it basically became the law of the universe. The idea was simple. Every piece of matter in the universe pulls on every other piece of matter. The bigger the object, the harder it pulls. The closer the objects are, the stronger the pull. That is it. One rule. And with that one rule, scientists could explain almost everything. Why does the moon go around the Earth? Because the Earth pulls on it. Why does the Earth go around the sun? Because the sun pulls on it. Why does an apple fall from a tree? Because the Earth is pulling it down. Simple, clean, and powerful. But the really amazing part was not just explaining things people could already see. Newton's equation could predict things no one had ever seen before. In the 1800s, astronomers were watching a planet called Uranus. It was not moving the way it should. Its path around the sun kept drifting, just a tiny bit away from what Newton's math predicted. Something was off. Now, most people would have said the equation was wrong, but two mathematicians had a wild idea. What if the equation was perfectly fine? What if there was another planet out there, one nobody had ever seen, and its gravity was pulling on Uranus? They sat down with nothing but Newton's equation and a pile of paper. They calculated exactly where this invisible planet should be hiding in the sky. In 1846, an astronomer named Johann Galle pointed his telescope at that exact spot. And there it was, a brand new planet. We call it Neptune. Think about that for a second. Scientists found a planet they had never seen before. They did not use a telescope first. They used math. They used Newton's equation to figure out where the planet had to be. And it was right there, exactly where the numbers said it would be. That is the kind of moment that makes scientists trust a theory completely. And trust it, they did. For the next century, Newton's gravity guided everything. Engineers used it to build bridges. Sailors used it to predict the tides. When NASA launched the Voyager spacecraft in the 1970s, they used Newton's equation to plot its entire journey across billions of kilometers of space. The probe swung past Jupiter, used the planet's gravity like a slingshot, and flew all the way to the edge of the solar system. Every move was calculated with Newton's math, and every single one worked. When a theory lets you discover hidden planets and fly robots past Jupiter, you stop questioning it. You just believe it. And for a very long time, nobody had any reason not to. But here is the thing about science. Sometimes the smallest crack can bring down the biggest wall. And there was a crack. It was tiny, almost invisible, but it was there and it refused to go away. If this kind of stuff fascinates you, hit that subscribe button. This channel breaks down the biggest, most mind-bending ideas in science and makes them actually make sense. We have a lot more coming, and you do not want to miss what is next. The tiny crack that broke everything. The problem was Mercury. Mercury is the closest planet to the sun. It races around in a tight orbit faster than any other planet. And like all the planets, its path is not a perfect circle. It is more like a stretched out oval. Now, here is where it gets interesting. That oval does not sit still. It slowly rotates. Very, very slowly. Each time Mercury goes around the sun, the oval shifts just a tiny bit. If you could speed up time and watch it from above, you would see the orbit slowly spinning like the hand of a clock. Astronomers expected this. The gravity of Venus, Earth, Jupiter, and the other planets all tug on Mercury a little bit. Those tiny tugs add up and cause the orbit to rotate. Scientists used Newton's equation to calculate exactly how much the orbit should shift. And they got really close to the right answer. Really close. But not perfect. There was a leftover. A tiny extra shift that the math could not explain. About 43 arc seconds per century. That is an incredibly small number. 1 arc second is 1/3600th of a single degree. So 43 arc seconds over 100 years is almost nothing. But it would not go away. Decade after decade, better telescopes, better measurements, and the same stubborn number kept showing up. Mercury was drifting just a little more than Newton's theory said it should. So what did scientists do? The same thing that worked with Uranus. They assumed there must be a hidden planet. This time, the mystery planet was supposedly hiding between Mercury and the Sun, too close to the Sun's blinding light for anyone to see it. They even gave it a name, Vulcan. For decades, astronomers searched for Vulcan. They organized expensive expeditions across the world. They watched during total solar eclipses, when the sun's light was blocked and the sky went dark. A few people even claimed they saw it, but every single sighting turned out to be a mistake, a smudge on a lens, a distant star, wishful thinking. Vulcan did not exist. There was no hidden planet. And that left scientists with a very uncomfortable thought. What if the problem was not a missing planet? What if the problem was the equation itself? What if Newton's theory, the greatest equation in the history of science, the one that found Neptune and guided Voyager, was not quite right? It seemed almost impossible to believe, but the numbers did not lie, and sometimes the smallest mistakes point toward the biggest discoveries. The happiest thought in history. While astronomers were still looking for a planet that did not exist, a young physicist named Albert Einstein was thinking about something completely different. He was thinking about light. In 1905, Einstein figured out something that would change everything. He showed that the speed of light is the fastest anything can possibly go. Not just fast, the fastest. Nothing in the entire universe can beat it. Not a rocket, not a signal, not any kind of information. The speed of light is the universe's absolute speed limit, and there are no exceptions. Now, here's why that creates a huge problem for Newton's gravity. In Newton's version of gravity, the pull between two objects happens instantly. No delay, no signal. It just happens. If the sun suddenly disappeared, right now, in Newton's world, the Earth would immediately fly off into space. The pull would vanish everywhere in the universe at the exact same moment. But Einstein had just shown that nothing can travel faster than light, and light from the sun takes about 8 minutes to reach Earth. So if the sun vanished, we would still see it shining for 8 more minutes. Its light would still be on the way. And if gravity also has a speed limit, then the Earth should keep orbiting the sun for those same 8 minutes before anything changes. Newton's gravity had no way to explain that. In his theory, there is no delay, no signal, no messenger, carrying the gravitational information from one place to another. The pull just exists everywhere, all the time, instantly. Even Newton himself knew this was a problem. He once wrote that the idea of objects pulling on each other across empty space without anything connecting them was so strange that no serious thinker should accept it easily. But the math worked, so everyone moved on. Now Einstein was saying that you could not move on anymore. If nothing travels faster than light, then instant gravity across empty space is impossible. Newton's theory was not just slightly wrong, it was missing something fundamental. So Einstein started asking a very different kind of question. Not how strong is the force of gravity, but what is gravity really? And one day, he had what he later called the happiest thought of his life. It started with a simple question. If you were inside a closed box with no windows, floating in deep space, and someone started a powerful rocket engine on the bottom of the box, what would happen? The box would start accelerating upward. You would feel your feet press against the floor. If you dropped a ball, it would fall. If you jumped, you would come back down. Now here's the key. You would have absolutely no way to tell the difference between that rocket pushing you upward and standing on the surface of the Earth. The feeling would be identical. The ball falls the same way. Your weight feels the same. Everything behaves exactly the same. Einstein realized this was not just a coincidence. If acceleration and gravity feel identical, maybe they are the same thing. Maybe gravity is not a force pulling you down. Maybe it is something else entirely, something built into the fabric of the universe itself. And this is where the story gets wild. If gravity and acceleration are truly the same, then gravity should do everything acceleration does, including something very surprising. It should bend light. Here's why. If you are inside that rocket and a laser beam shoots across the box from one wall to the other, the box is accelerating upward while the light crosses it. So by the time the light reaches the far wall, the wall has moved up a tiny bit. Inside the box, the light looks like it curved downward. Now, if gravity and acceleration are the same thing, then gravity should bend light the exact same way. A beam of light passing close to a very heavy object should curve. This was a bold prediction because Newton's gravity would never bend light. In Newton's world, gravity only pulls on things that have mass. Light has no mass, so light should fly straight past any object, no matter how heavy. Einstein said no, light should curve near heavy objects. And in 1919, there was a chance to test it. That year, a total solar eclipse was going to darken the sky long enough for astronomers to photograph stars that appeared very close to the edge of the sun. If Einstein was right, the sun's gravity would bend the starlight, making those stars look like they had shifted slightly from their real positions. An astronomer named Arthur Eddington organized expeditions to photograph the eclipse. When the results came in, the stars had shifted, and the amount of the shift matched Einstein's prediction almost perfectly. Newspapers around the world ran the story. Newton's gravity had been overthrown. Einstein became the most famous scientist on the planet almost overnight. But the bending of light was just the beginning. The real surprise was what Einstein's theory said about gravity itself, and it is stranger than almost anyone expected. What gravity actually is here is the big reveal. Einstein's theory says that gravity is not a force, not even a little bit. There's no invisible rope between the Earth and the Sun. There's no mysterious pull dragging the moon around in circles. None of that is happening. Instead, heavy objects change the shape of space and time around them. That sounds wild, so let me break it down. You probably think of space as empty and flat, like a giant invisible room that everything moves through. And you probably think of time as something that ticks along at the same speed everywhere, like a universal clock. Einstein said both of those ideas are wrong. Space is not flat. It can bend, stretch, and curve, and time does not tick at the same rate everywhere. Near heavy objects, time actually runs slower. These are not ideas or guesses. They have been measured. They have been proven. They are happening right now, all around you. Let me give you an example that affects your life every single day. The GPS satellites orbiting the Earth are about 20,000 kilometers above the surface. Up there, gravity is weaker. And because gravity is weaker, time runs slightly faster on those satellites than it does down here on the ground. The difference is about 38 millionths of a second every day. That sounds like nothing. But GPS works by measuring time with extreme precision. If engineers did not correct for that time difference, your location on your phone would drift by about 10 kilometers every single day. Your map would show you in the wrong city. The fact that your GPS actually works is proof that Einstein was right. Time really does run at different speeds depending on where you are and how much gravity is around you. Now, here is how that connects to gravity. Everything in the universe is always moving through time. Even when you are sitting perfectly still, you are moving forward through time. Your watch ticks, your hair grows, you get older. Time is always flowing. But near a heavy object like the Earth, time flows a little slower close to the surface and a little faster farther away. This creates a kind of slope in the universe. Not a slope you can see, but a slope in the way time flows. When you release a ball from your hand, the ball does not get pulled by a force. It simply moves along the easiest path through this time slope. That path curves toward the Earth, because that is the direction where time runs slower. The ball is not being dragged. It is coasting. It is doing the most natural thing an object can do. And here's a way to think about it that makes it click. Think of two people standing on the equator of the Earth a few meters apart. They both start walking straight north. Neither one turns. Neither one aims toward the other. They both walk in perfectly straight lines. But the Earth is round. And because the surface is curved, their straight paths slowly get closer and closer together. Eventually, they meet at the North Pole. If you did not know the Earth was round, you might think some invisible force pulled them together. But there is no force. They walked straight. The surface beneath them was curved, and that curvature made their paths come together. That is exactly what gravity does. Heavy objects curve the space and time around them, and everything nearby simply follows the straightest path through that curved space and time. Planets are not being pulled around the sun. They are following the straightest paths available to them through curved space-time. And those paths happen to be orbits. Now remember Mercury? The tiny leftover shift in its orbit that nobody could explain? The one that sent astronomers on a wild chase for a planet that did not exist? When Einstein finished his new theory in 1915, one of the first things he did was calculate Mercury's orbit using his new equations. And the answer came out to exactly 43 arc seconds per century. Not approximately, exactly. The number that had puzzled astronomers for over 50 years just fell straight out of the math. Einstein later wrote that when he saw that result, his heart started pounding. He knew he had found the right answer, and the theory did not stop there. If space-time can curve, then it can also ripple. When two massive objects crash into each other, they send waves through the fabric of space-time itself. These are called gravitational waves. Einstein predicted them over 100 years ago, but they are incredibly hard to detect. The ripples are unbelievably tiny. In 2015, a detector called LIGO finally caught them. Two black holes had smashed into each other more than 1 billion light-years away. The collision was so powerful that it shook the fabric of space and time across the entire universe. When the ripple reached Earth, it stretched and squeezed space by a distance smaller than the width of a single atom. And the detector measured it. The signal matched Einstein's prediction perfectly. Space-time really does ripple. And speaking of black holes, they are maybe the most extreme example of what gravity really is. A black hole is not like a giant vacuum cleaner sucking things in. In Einstein's picture, a black hole is a place where space-time is so deeply curved that every possible path leads inward. There is no direction that points back out. Not because a force is holding things in, but because out simply does not exist there anymore. Even light cannot escape, because there is no path for it to follow that leads away. All of this comes from one idea. Gravity is not a force that pulls things together. Gravity is the shape of the universe. Heavy objects bend space and time, and everything else just follows the curves. So the next time you drop something, look at it differently. That object is not being pulled to the floor. It is simply following the easiest path through a universe that has been curved by the mass beneath your feet. And you, standing there on the ground, you are the one being pushed. The floor is stopping you from following your natural path. That pressure you feel on the soles of your feet is not gravity pulling you down. It is the ground forcing you to stay still when the universe wants you to fall. The falling object is the free one. You are the one being forced. If this video gave you a new way of seeing the universe, hit that like button and subscribe if you have not already. We have got a lot more coming. Now, here is something I want you to think about. Einstein's theory replaced Newton's and gave us a better picture of gravity. But even Einstein's theory has limits. It breaks down inside black holes and clashes with quantum mechanics. So if Newton was not the final answer, and Einstein might not be either, what do you think comes next? Drop your thoughts in the comments. And if you want to keep going down the rabbit hole, check out this video right here.